Hello and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Yay, it's true. And I'm Corinne Caputo, a writer, funny person, and friend to the world.
You are a funny person. You make me laugh all the time.
Aw, thank you, Moiya.
And I know you make other people laugh too, yeah. So like Corinne said, I am Moiya. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and friend to the universe. And I am not a professional comedian. I am not funny professionally, but I did stand-up. I did stand-up last weekend.
How was?
It was my third time ever doing stand-up, my first time in 4 years, and I did not make an utter fool of myself. It actually went pretty well.
I'm sure you didn't. When we would co-host my astronaut training show together, I felt so safe and excited. Because you are you're very quick and you're very confident. And that, I think, is all you need to be on stage.
Oh, thank you. Thank you. It helped. First of all, the vibes for this venue, absolutely immaculate. It was at Women's World of Boxing. I'm going to do a quick plug because they're awesome.
Cool.
It is the first, and I think still only, all-women's boxing gym in New York City.
Oh, cool.
So we did the stand-up in the ring. I'm standing behind the
God.
bands. I had to crawl in through the bands to get to the boxing ring.
Okay, how hard is it to pull those apart? Because it feels like I just can't tell.
It actually is not that hard. They're pretty stretchy.
Okay.
Yeah, they move. So I was able to get in, and then the mic was one of those 1940s metal mics. It didn't move
like
from
Mrs.
the stand.
Maisel?
Like Mrs. Maisel.
Yeah.
Yeah, I felt awesome doing that set. So that helped with the confidence a lot.
That's really fun.
Mm-hmm. And the universe witnessed the set and was happy with me for it because it's a good bud. But we are not recording this episode in that boxing gym, again, Women's World of Boxing on the Upper East Side of New York. We are recording this episode very far from that boxing gym. We are in the Great Plains. We are in a vast grassy plain. It's nighttime, actually. The stars are above us, and we are sitting next to a crackling campfire. And I know that we can't see it, but the topic of today's episode will probably pass above us at some point while we're recording, because we are talking about the Hubble Space Telescope.
Yay!
Yay! I grew up hearing about Hubble. I have never requested Hubble data, but I've played around with it in my time at grad school. And this day that the episode is being released on, it's fortuitously exactly 33 years after Hubble launched on April 24th, 1990.
Oh, yeah. Isn't 33 the Jesus year?
I don't even know what that means. The Jesus year?
The Jesus year. Isn't it you're in your Jesus year? Actually, this is so depressing now that I'm explaining it. I'm pretty sure it's that's the year he was crucified. He was 33.
Oh,
okay.
No.
I'm trying to say it in an exciting way. Isn't that a special number? But now it sounds sad. So.
Well, okay, fine. Hubble is in its Jesus year. And yeah, we're here to talk about Hubble, the long story of how it was created and built and launched into space, because we don't just decide to make a telescope and then send it right up. Mm-hmm. It takes a long time. And then we're going to talk about some of Hubble's really exciting discoveries that it's made in the last 33 years, guys. That
is a lot of work.
That's so much work. We're gonna talk about some of its stats, but truly, this is an incredible machine. It is actually the first optical space-based observatory that can send data back to Earth that we ever launched into space. It is
wow.
This is a seminal piece of technology. So I'm very excited to be talking about Hubble today. And I think this is going to be the first in a series, not consecutive, but we're going to be talking about a lot of telescopes and observatories throughout the rest of Pale Blue Pod's episodes. We're going to start with the first.
I love it.
Yay. All right, so let's get into the history. How did the Hubble Space Telescope become a thing? And throughout this, if I get tired of saying Hubble Space Telescope, I might shorten it to HST, which is what a lot of astronomers do. So just, so you're in the know with my lingo.
Noted.
So like I said, it launched exactly 33 years ago today on April 24th, 1990. But the origins for this go all the way back to 1923. That's where I'm going to start this story. Because in 1923, a German physicist named Hermann Oberth, who was one of the fathers of modern rocketry. I don't know why I said modern rocketry like there's ancient rocketry, but...
Well, the ancient rockets had a big part.
So big. We truly were launching these modern rockets on the shoulders of those giant ancient rockets.
Depends how much Ancient Aliens you're watching late at night.
Boo. Big boo to Ancient Aliens over here. So in 1923, Hermann Oberth published a paper called Die Rakete zu den Planetenraumen, which is the rocket into planetary space. And in that paper, he described how a rocket could be used to take a telescope from the surface of Earth out into Earth's orbit. Before that, people just weren't thinking about putting telescopes into space, or at least they weren't writing about it.
Yeah, that makes sense.
Yeah, that's 1923. A full 23 years later, in 1946, World War II is over. People are starting to think about putting satellites up into space, but not necessarily telescopes. And an astronomer named Lyman Spitzer. To any astronomers out there who are listening, both of those words should sound familiar to you. Lyman, from these Lyman alpha lines, that's a spectroscopy thing that we might cover in a future episode. And Spitzer did become a telescope, an infrared telescope. So Lyman Spitzer, who must have done a lot of cool science because his name gets used in science.
It's a great name.
It's a great name. He wrote a paper called Astronomical Advantages of an Extraterrestrial Observatory, where he pointed out 2 reasons why we should start putting telescopes out into space. One of those reasons is that our atmosphere blocks a lot of ultraviolet and infrared light from space. The light, when it's coming through our atmosphere, it will get scattered by different particles, or it will get absorbed by different molecules in the atmosphere. So if we're just using land-based telescopes, we're going to be missing a lot of UV and infrared radiation.
That makes sense.
That does make a lot of sense, yeah. So X-ray missions actually have to be above Earth's atmosphere. We either fly them on high balloons or on airplanes, or we just send them out into space. But the other reason that you want space-based telescopes is because our atmosphere, even in other wavelengths of light, is really turbulent. The water vapor, the clouds, just like the wind in our atmosphere will interfere with light paths coming from space. We call it aberrations, aberrations of light, where the light just gets like woo 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 as it's coming through space.
The technical term. Yeah.
That's the sound that I think light makes when it's passing through our atmosphere.
Yeah, that when the few science classes I took, I remember learning that.
Yes, so that's 1946. Thanks, Lyman Spitzer. Following the launch of Sputnik in 1957, which was the first satellite that the USSR launched into space, NASA, it's a very young NASA, it launched 4 UV telescopes out into space called orbital astronomical observatories, and they launched these OAOs between 1966 and 1972.
That's when we were heading to the moon.
You're right.
Same time.
Yes, that is. So NASA was very busy in the 60s.
Yeah.
It was trying to get people to the moon. It was trying to win the space race. Mm-hmm. And so we were putting things out into orbit, but not yet an optical telescope. And so in the meanwhile, from 1966 to 1972, and also kind of from 1946 when he published that paper, Lyman Spitzer has been gathering support for a large multi-wavelength orbiting observatory that at first it was going to be called the Large Space Telescope, because we've always been so good at naming things.
Of course. The LST?
Large Space The LST, yes. So in 1969, the LST was officially approved for production by the National Academy of Sciences.
Wait, this reminds me of that scale we talked about where they started with I think it was for stars, where it was they started with the number and then found things that were below what they thought was the baseline.
Oh, yeah, the magnitude system.
Yeah, so it's the Large Space Telescope on what scale? Because we're going to have the larger space telescope one day, or
The most ridiculous telescope name that I have come across is the Overwhelmingly Large Telescope. We will continue to come up with other adjectives.
Keep having big names for that. Yeah, that's so funny.
Yeah, and there's a reason we want our telescopes to be larger. The bigger the telescope is, the more collecting area it has to gather light, and the better our resolution is, which means we can see things that are closer together and we can tell them apart. But this is going to be called the Large Space Telescope, and it officially got the green light in 1969, which is the year we went to the moon. And then for some reason, right after we achieved this huge milestone, this huge accomplishment, NASA gets their budget cut.
Of course.
So in the 70s, after all of this success, NASA budget cuts slowed down the production of the Large Space Telescope. And the project was literally downsized. Originally, it was going to be a mirror that was 120 inches across, so 12 feet across. And because of budget cuts, that got pushed down to 94 inches across, which is what it ended up being. And then also because of those budget cuts, the European Space Agency was brought on as a collaborator in 1975. They contributed roughly 15% of the funding in the form of a specific camera. So they contributed the faint object camera, which is a specific instrument on this telescope. And they also contributed the solar arrays that power these instruments on the telescope. And in exchange for that 15% of funding, the European Space Agency was guaranteed 15% of the observing time on this telescope. So now, because of their contribution, 15% of the time on this telescope has to go to European astronomers.
Okay.
Which I think is fine.
Yeah, that makes sense.
So that's 1975. 8 years later, in 1983, they were ready to go with the Large Space Telescope. They established the Space Telescope Science Institute in Baltimore, Maryland. It's kind of attached to Johns Hopkins University. I call it just Space Telescope, or STSCI is what a lot of astronomers call it. So they established that base to operate the Large Space Telescope, but then cost and engineering issues got in the way and pushed the launch for the LST back to 1986. I don't know if you know anything about space in 1986, Corinne. Do you know what happened in 1986?
Yeah, so the Space Center is a Challenger learning center. So the foundation of the Space Center is in honor and memory of the Challenger mission, which happened in 1986 and very sadly lost the lives of the whole crew. And Krista McAuliffe was one of the astronauts on that trip. She was a science teacher for I think at elementary school. But the Challenger Center was founded in her memory to continue science education for youth.
Oh, that's heartbreaking.
Yeah.
So
really sad.
This is one of the saddest moments in space history,
yes.
I think, is the Challenger explosion. So that happened in 1986. Obviously, they weren't going to launch this telescope right after that because they didn't have a shuttle to take it up. A lot of space stuff shut down after Challenger happened. So then it was officially launched 4 years later in April of 1990. In total, it took 21 years, 12 different countries, multiple NASA sites around the U.S., and $1.5 billion of 70s money to make and launch the Hubble Space Telescope. Along the way, the name got changed from the Large Space Telescope to the Hubble Space Telescope in honor of Edwin Hubble, who discovered a lot. One of the things he is credited with is discovering that we live in a galaxy in the first place, that we are one galaxy in the universe, and that the universe is expanding. We often credit that knowledge to Hubble. And then we named a telescope after him. Hubble, through those 21 years of development, it was intentionally made to house multiple instruments that could be repaired in space instead of bringing the telescope back to Earth to fix and then send back up. Because it's really expensive to launch and capture different things in space. And so it was built so that astronauts could go out to the Hubble Space Telescope and fix it where it is, which I think is really cool.
That's perfect.
Have we talked about the difference between telescopes and instruments before?
I don't think so. Maybe not certainly not in detail.
Okay. Do you have any, what do you think would be the difference there?
Telescope and instruments. Well, instruments just feel smaller to me. I don't know if that is true.
That's fair. Yeah, they are smaller.
But telescopes they're not exclusive to being in space because you can have a telescope at home.
Right.
Yeah.
Right.
I don't know.
Yes. This isn't something that a lot of people think about because astronomers just talk about looking through telescopes. But really, a telescope is a big light bucket. Its job is to collect the light, and then it sends that light into instruments which will manipulate and analyze that light for different things. So a spectrograph is an instrument that takes light from a telescope, splits it up into its different wavelengths, and then tells you how much power there is at the different wavelengths.
Cool.
But there are lots of different types of instruments, and Hubble was made to hold multiple. I think at any given time it can have 6 instruments on it.
Whoa.
Mm-hmm. And it's really good that Hubble was made to be fixed in space because it needed to be repaired almost immediately.
Oh, no.
Because after 21 years and $1.5 billion, they launched this thing into space with the promise that it's going to take the most beautiful pictures of the universe that we've ever seen, and it's going to help us look back to the beginning of the universe. And they take the first images with Hubble, and they're so blurry that they're almost useless.
No.
The whole point of Hubble was that it was supposed to take these gorgeous pictures, and they send back blurry images. And they found that it's because the primary mirror on Hubble, and I'll tell you what that means in a second, but the most important mirror on Hubble was just the teensiest fraction of an inch out of shape. The edges of the mirrors were just a little bit too thin. And so it created this fuzziness, this blurriness in all of their images. And so in 1993, NASA had its first service mission up to Hubble where they couldn't replace the mirror because it's too big. It's almost 8 feet across.
Whoa.
So they can't replace the mirror, but they did replace an instrument on the telescope. And that instrument had essentially coding in it that would correct for the shape of the mirror.
Cool. That feels like eyeglasses. Where they're kind of bent just perfectly for you to be able to see.
Exactly, yeah. So it wasn't until 1993 that we really got the first useful images from Hubble.
Also, I'm imagining how I know how expensive it is to buy yourself a nice mirror. I can't imagine how expensive it was to need to repair a mirror in space.
Oh, yeah. The mirrors for telescopes are some of the most expensive parts of building it. The mirror for JWST, first of all, it's so big that it's not a continuous mirror. It's segmented. So it's like a fly's eye of mirrors,
Whoa.
Many of them put next to each other to make a bigger picture. It's beautiful. So that's the story of how Hubble got launched and how we had to immediately fix a terrible mistake that no engineers caught, which I love because even the smartest people working at NASA make mistakes that cost billions of dollars.
Yeah, for sure.
And that's fine because we're humans. But we learned a lot.
It's good to hear that.
So I now want to tell you a bit about Hubble itself, some of its facts and numbers. Hubble orbits about 340 miles above Earth's surface. It is not in what's called a geosynchronous orbit where it's above a specific part of Earth. Instead, it orbits Earth, and it orbits about 15 times every single day. It takes it 90 minutes to go around the planet. It's zipping.
That's
out there.
Really fast. Well, I'm pretty sure that's close to the speed of the ISS.
Yeah, that makes sense.
Yeah.
I don't know where they are in relation to each other, but there aren't a lot of places that you can put something to have a stable orbit around Earth. There are different, we call them Lagrange points, and those are points where gravity works out to be stable for different types of objects. And I'm sure that the ISS is at like one of those Lagrange points, and Hubble probably is too. So they might be near each other.
I'm trying to Google it to find a quick answer, and I don't have it.
No, I think that would be a tricky one to find because they're moving.
Yeah.
So. But yeah, it does orbit Earth every hour and a half. And Corinne, how big do you think Hubble is? How big do you think this telescope is?
There's no way I'm right, because have you ever seen like one of the, like a stop sign knocked down or something, or like a street light knocked down?
Oh, they're huge.
They're huge. They are so much bigger than I think they are. Just because they're a few feet above my head, I'm like, I've decided that this is that size, and like, I've never been on eye level with it before. So if I'm wrong about that, I'm going to be wrong about Hubble. I just know it.
Yeah. I'm prepared for you to be wrong, but that's fine.
If the mirror is like 8 feet across, I feel like it's got to be like, is it smaller? Is it larger than a car? Like a truck?
There you go. Yes. Yes. So it is approximately the size and weight of a school bus.
Oh my God. Okay.
Yeah. The Hubble Space Telescope weighs 27,000 pounds.
Wow. Heavy.
It's so heavy. It's a big boy.
Yeah.
I love that about it. I also didn't realize how big it was until I went
sense.
searching for this information.
Something we said a lot at the Space Center was that the space shuttle, which was like, you know, the main ship you're probably picturing when you picture a rocket, could fit a school bus inside, like the part that would open up where they would carry up pieces of the ISS. So that makes sense if it was in the era of the space shuttle.
Yeah, I think it was carried up by Discover.
Yeah, that makes sense.
So the HST sees from the infrared part of the electromagnetic spectrum all the way to the ultraviolet part. So go listen to our electromagnetic spectrum episode if you don't know what that means. But here's how it works. So light comes in from one end of the telescope, and it does have this cool little like door that it can shut when the telescope is facing the sun so that it can charge its solar panels without damaging the mirror, because like too much light would damage the mirror. So there's this door that can be open or closed. Light will come in from one end of the telescope, whatever it's pointing at. It'll hit the primary mirror, which is about 7.8 feet across, so 94 inches across. That light bounces off of the primary mirror and hits the secondary mirror that is actually closer to that trap door. So the primary mirror is further away, and then it bounces off the primary mirror to hit the secondary mirror, which is just 12 inches across. And then the light bounces from the secondary mirror through a hole in the middle of the primary mirror to get focused into the instruments so that the light can actually be analyzed.
Cool. It feels similar to like the shutter of a camera or like a pinhole camera, if you ever did that experiment.
Oh, what's a pinhole camera?
It's like creating a really tiny hole. You kind of make it out of like a cardboard tube and like tinfoil, and then you put like a pinhole size in one end to like, quote, take a picture. And it's like a very crude version of a camera, but it kind of explores how small a shutter could be. I hope I'm getting this right. I could be wrong.
Oh, that's
but I
very
remember
cool.
that kind of like STEM type experiment.
That will definitely be in this week's research notes. But that is how a lot of telescopes work. You know, there are different ways to make a telescope, but a lot of them are extremely similar to cameras. You know, a lot of, like the CCD, the charged coupled device, it's this array of pixels that actually like takes the picture in most modern cameras, like in our phones. I think the CCD was in large part developed for astronomy, like for space telescopes.
Oh, cool.
Or like not space-based telescopes, but
Yeah.
telescopes that would look at space. Yes. So that's the light path that photons have to travel through the Hubble Space Telescope, which is really cool. Because the primary mirror, the big light collecting area for Hubble is so big, its resolution is about 1,000 times better than the human eye. And so I looked up a comparison on the NASA website, and it said that the resolution on Hubble is, and I quote, good enough to resolve 2 fireflies separated by about 10 feet from the distance between New York City and Tokyo, end quote.
Whoa.
So from that far away, you can tell apart two fireflies that are 10 feet away from each other. That is how good the vision on the Hubble Space Telescope is.
Very clear.
Amazing.
I can't imagine being able to see that well.
I mean, well, that's why we have all of these gorgeous images from Hubble that we'll talk about at the end of the episode.
Hi, it's Corinne. Welcome to this episode's mid-break. We had to stop recording because this fire is about to go out and Moiya is off finding more firewood. So this is a great time to give a shout out to our patrons who support this podcast every single month. So thank you, as always, to our sun-like stars, Sharn Llewellyn, Finn, and Peyton. And thank you to our latest patrons, Jessie Esparza and Katie Hammond. We're so thrilled you're here. You too can support us, hear your name on this pod, and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. You can find the star chart, Patreon info, and more at our website, palebluepod.com, or go right to the source at patreon.com/palebluepod. And if you can't support us financially, that's totally fine. We love you still. Thank you for listening. You can support us by sharing the show with your friends. Okay, and I want to tell you about Brilliant.org. If you want to learn more about science or math or AI technology, whatever level you're at, Brilliant will help you master the skills you need. Brilliant is the best way to learn about things like math and computer science interactively. There are thousands of lessons from foundational and advanced math to AI, data science, and more, and new lessons get added monthly. So even as a copywriter, I really need to know the ways to stay ahead in this industry, especially as it's getting affected by AI and all the little computers that are now writing things. The skills I learned to build my career aren't exactly the skills I need now, but this is where Brilliant.org comes in. So I'm a big believer in hands-on learning, and Brilliant's visual hands-on approach is such an effective way to master the key concepts behind today's tech. Plus, it's perfect for busy people with bite-sized lessons that break down important concepts into understandable parts, kind of like what we're doing here at Pale Blue Pod. So try everything Brilliant has to offer for free for a full 30 days just by visiting brilliant.org/palebluepod or click the link in our description. The first 200 signups will also get 20% off Brilliant's annual premium subscription. Again, that's brilliant.org/palebluepod. And finally, in more fun news, I want you to consider supporting your friendly local podcast collective. Pale Blue Pod is a part of Multitude Productions, a small business that helps creators make a living in the modern media landscape, which is no small feat. So for $5 a month, you get Multitude's weekly friendly debate podcast, access to Multitude's pen pal exchange, monthly live events with hosts, including me and Moiya, and so much more. Your dollar goes further when you support indie creators like us, so please consider it. Whether you spread the word or spread the love with your dollars, shop small, support Multitude today and every day. You can learn more at multitude.productions/multicrew. Now back to the episode.
So there are, I said before, 6 instruments on Hubble at any given time. Right now, the 6 instruments are, and they have been for a while because the last service mission was in 2009. So right now, the instruments on Hubble are the Wide Field Camera 3, so like the 3rd iteration. And this wide field camera is responsible for most of the famous Hubble images, like the Pillars of Creation, the Horsehead Nebula. That's done with this camera. It's just a camera that has a very wide field of view, so it can see like a lot of space at once. Then there is the Cosmic Origins spectrograph. This is an ultraviolet spectrograph that's best for observing single points of light, like a star or a quasar, an active galactic nucleus we've talked about before, so like a shining black hole, or even very distant galaxies. That's what the COS is for, the Cosmic Origin Spectrograph. Then there's the Advanced Camera for Surveys, which is an optical instrument, so it looks in our visual range of the electromagnetic spectrum. There is the Space Telescope Imaging Spectrograph, or STIS for short, and it combines a camera with a spectrograph, so it provides, NASA said, like a fingerprint of a celestial object's temperature, chemical composition, density, and motion. So you can get a lot of really valuable information through the STIS instrument. Then there's the near-infrared camera and multi-object spectrometer. That's another camera plus spectrometer combined. And finally, there is the fine guidance sensors to keep the telescope on target. Because the telescope is moving, the stuff in space is moving, so you need to have these things that can sense where the object is and where the telescope is pointing so that it's always looking where we want it to look.
Yeah, good.
Yeah. That's just a nice array of instruments that have given us so many scientific discoveries. Hubble sends data back to Earth every day in radio wave transmissions. It sends about 18 gigabytes of data every single week.
Whoa.
So much data.
That is a lot.
Like, imagine the storage that the Space Telescope Science Institute has to have to store all of Hubble's data. And now STSCI is also the home base for JWST, so it has to store all of
that data.
JWST's data too. It's just like so much storage.
Think of the fans running in that room of computers.
Oh, yeah. So many fans. I've been in some telescope data management centers that have like, those rooms are cold. I don't think it's just AC. Like, some of them use like high-tech cooling systems that use like liquid nitrogen or something.
Yeah.
Like they get fancy with it.
It's too valuable to be whatever's going on in my laptop.
Yeah, absolutely. So Hubble has now been acting for exactly 33 years. Originally, they intended this mission to last 15 years.
Whoa, more than double.
It's more than double. Yeah, more than doubled its lifespan. And so now, after 33 years, it's made more than 1.5 million observations, and data from the Hubble Space Telescope has been used to publish more than 19,000 peer-reviewed scientific articles.
Wow, that is a helpful tool.
Right? And to think, it took like 20-something years for it to get made. This was one of the first... It was like really the first space-based astronomical observatory, not counting those 4 little UV machines. And it was a really good test to show us what we could do if we put a telescope out in space. And now we've put a bunch of them up there.
Yeah.
I want to talk a bit about what it's like to use Hubble as an astronomer, because, it's not like any average Joe astronomer can walk up to it and like put their eye in the eyepiece.
Right.
Not that you can do that with any Earth-based big telescope either, but like you really can't do it with Hubble. And so instead, astronomers have to apply for time on the Hubble Space Telescope by submitting proposals for their observation. So Space Telescope Science Institute, the base for this telescope, they will put out a call for proposals, and astronomers will very frantically work on these proposals up until the deadline, and then they'll submit to Space Telescope. Something called a TAC, a time allocation committee, goes through all those applications and decides who's going to get time on that telescope, keeping in mind that 15% of it has to go to European astronomers. And then winners are chosen. And those astronomers who were awarded time, they then have to submit a second proposal, which is a more polished version of their observing plan. And then Hubble will schedule the observation and observe the data. Sometimes, you don't have to worry about getting clouded out or rained out because it's not on Earth. So that type of weather isn't going to affect you, which is really nice.
That is great.
But it is kind of this cool, almost like Tetris-like exercise of trying to fit together all of the observations for this telescope because, you can only observe an object when it's in the right orientation with respect to us.
Right. The scheduling of that must be wild.
Wild. Because it has a whole year's worth of time.
Yeah.
And they don't want to waste any time on the Hubble telescope. Right. So it's packed with observations. Yeah, you really want to
optimize what it's looking at and who's looking at it. And so is the other 85% of time, is that up for grabs for anyone? Mm-hmm. It doesn't have to be a specific
American astronomers.
Yeah.
No, I'm pretty sure it's anyone.
Cool.
Mm-hmm. And then after the observation is done, the data gets sent to the astronomer who requested it, and they have these cool pipelines to like clean the data, is what we call it, just like removing any outliers or putting it into a form that astronomers actually want to work with it in. So there's that whole process. And the astronomer who requested the data, they have like proprietary access to this data for a year, and then it becomes public. Which is good, because you don't want those astronomers to get scooped. You want them to have time to actually publish results with their data. But there's a workaround to this, because Hubble is operated by NASA, which is a federal organization funded by taxpayer money. Like, they have to say what they're observing. Like, they have to say what they're doing. And so you can always see in real time what the Hubble Space Telescope is observing. The way that I do that is actually through a Twitter bot account called Space Telescope Live. And so it'll just tweet like, HST is observing quasar name, insert name here, for Dr. So-and-so. Like, it says it's observing and who the observation is for, like who submitted the proposal. So you can always know what they're looking at, but you won't necessarily have the data for a year. But this has gotten some people in trouble before. Like, I know that my advisor, David Kipping, who I've talked about before, and Alex Tichy, they were looking for exomoons, and they requested Hubble time to do a search for exomoons, which are moons around exoplanets. And they got their data. They had a year to work with it. But someone saw that the Hubble Space Telescope was looking at this particular exoplanet system. And they saw who requested the time. They saw it was Alex Tichy. And they're like, oh, Alex does exomoons. That must mean they're looking for an exomoon around that planet. And then Alex and David had to like really hurry up to put out their paper.
I was going to say, did they get scooped?
They did not get scooped, but they almost got scooped.
I hate to think that you could get scooped.
I know. It's some areas of astrophysics are pretty cutthroat in that way, where you it's extremely competitive and scooping is pretty common. I never had that issue.
Yeah.
Which is great. The current call for proposals from Space Telescope is cycle 31. Anyone can submit a proposal, and the deadline is May 24th, 2023. So anyone listening to this, you have a month to submit a proposal for Hubble time. But also, please do not just flood the application cycle with jokes. Yeah, because I have seen the effect. I have seen the toll it takes on astronomers to fill out these Hubble proposals. Like, it's a non-trivial amount of work. It's extremely difficult. Yeah. So anyone can.
Doesn't mean you should.
Take your best shot. Yeah, in the last 33 years, Hubble has revolutionized astronomy. We have learned so much about the universe thanks to this first observatory that we launched up into space. Not the least of which is all of those gorgeous images.
Oh my God, they're so pretty.
Yeah, so like so many of the NASA pictures of the day, astronomy pictures of the day, so NASA APOD, so many of those are Hubble images. I mentioned the Pillars of Creation, which is the Eagle Nebula, and it looks like these gorgeous like pillars of rainbow-colored gas out in space, and it's so nice to see. The Horsehead Nebula, where it's this cloud of gas that looks like a horse's head. So many of those images, thanks to Hubble. And I do think that a lot of people are interested in space because of those pictures. So I'm really glad that Hubble exists because, I want people to be interested in space so that I have job security. But that's like public interest in space, which is extremely important. But now I will also talk about some of the scientific discoveries. So one of them is that with the Hubble telescope, we were able to constrain the universe's age. Edwin Hubble, who this telescope is named after, I said before, he discovered pretty much that the universe is expanding, but he didn't know how fast, or he had an idea, but there were really large error bars on it. So before the Hubble Space Telescope, the measurements of the age of the universe varied from like 10 to 20 billion years. That's how big the error bar was.
Huge.
And the way you measure the age of the universe through the expansion rate is that if you know how fast the universe has expanded and you know how big it is now, you can kind of like reverse calculate how long it has been expanding. It's just like 1 over the expansion rate. So we even call the age of the universe a Hubble time because it was found by Hubble. And so now we have narrowed that universal age down to 13.8 billion years. Like we got a lot closer to the actual measurement because Hubble was so much better at getting crisp images of distant galaxies so that we could measure how fast they were moving away from us.
Cool.
Mm-hmm. That's redshift. That's they were doing redshift, and we did a whole episode about that.
Oh my God, I meant to text you because I went and got a drink on Friday night a few days ago, and I was sitting next to somebody on, I think, their first date, and he was explaining the universe's expansion and how like something red doesn't mean it's hot, and I almost was like, do I interrupt this date and be like, you gotta listen to my podcast? But I did not. But it was like the bar was kind of sort of crowded, so we were sharing a table with them.
Oh, okay.
So it wasn't like we were kind of breaking the like intimacy anyway by like needing to sit next to them, but I didn't interrupt, and I probably should have.
That would have been such a baller move, Corinne, if you had been like, well, I have this podcast.
I felt so, because it was like as soon as we sat down, and I was like, oh God, I would just like, they would get the totally wrong impression of who I am if I do this. But I was hoping they would keep going and I could like butt in later, but they were wrapping the date up and ready to go.
Oh, okay.
But there are 2 fans out there who may or may not know about us.
You know what, Corinne? Maybe that person learned that information from listening to Pale Blue Pod.
Oh my gosh. Okay, if you live in Portland, Maine.
That would make me happy.
And you were on a first date at Jewel Box the other night, and I sat next to you.
I'm so glad it was you sitting next to them and not me, because anytime I hear people talking about astronomy in public, I can't focus on anything else.
I'm sure. It was actually really, really hard.
And I've been that person.
I have a hard time not listening to who was ever around me, no matter what. Mm-hmm. But this felt like, kind of felt like a chance to gossip or like a chance to talk about myself. So I'm like, let's do it.
Here. The universe, after listening to like a couple episodes ago and how we both struggle with self-promotion, it was giving you an opportunity.
It really was. It really was.
I have obviously talked about astronomy stuff on first dates before, obviously. But I weirdly feel like I'm giving something away for free when I do that.
They need to be a patron. They actually need to be a Patreon.
I think every time I do it, I think like after we record, I had a first date right after we recorded the Redshift episode. Mm-hmm. And so then my date was like, so what have you been up to today? And then I told them everything I knew about Redshift.
That's so, you just did the podcast again.
Pretty much. And at the end, I was like, you know what? Normally people have to pay to hear me talk about science. You're getting a
Venmo request when you get home.
That's okay. You paid for the drinks, so it's fine. It worked out. Yes. So Hubble, thank you for helping us more precisely measure the age of the universe. The next thing I want to talk about is so important in our understanding of the universe, and it is the Hubble Deep Field. There were 3 Hubble Deep Fields, a regular one, a south one, and then an ultra deep field. And one of the first images to come out from JWST was its own deep field image. So I don't know if you've ever seen this. It's one of the most iconic astronomy images ever, but it looks like a black square with a bunch of like fuzzy points of light in it.
Yes, I have seen this picture. I will put it on our Instagram. I love this picture.
It's so good. And I think you'll love it even more when you hear the story behind it. So before the Hubble Space Telescope, we thought that the universe was a lot emptier than it actually is because we couldn't see any really distant or faint galaxies. Like we just didn't know they were there. And so there was actually this kind, like almost like a bet, not an actual bet, not like Stephen Hawking and Kip Thorne, but there was this astronomer in the 90s, right after Hubble launched, or maybe right before, who was doubtful that Hubble would be able to find any new galaxies. He was like, we've found all the galaxies. And so In 1994, the director of the Space Telescope Science Institute, Robert Williams, used his discretionary time on the telescope as the director to take this deep field image. As the director, he had 10% of time on Hubble that he just got to allocate however he wanted. So 15% to the Europeans, 10%.
Almost as much for the director. That's crazy.
10% of time on this multi-billion-dollar telescope. And so kind of in response to that bet, he had, for a couple of years, he had researchers at Space Telescope find what we thought was an empty patch of sky. He was like, look through all of our catalogs, figure out if there are any stars there or any background galaxies. I want an empty patch of sky. And they did. They found one. And for 10 days over Christmas in 1995 or 1996, Robert Williams pointed the most expensive telescope in the world at an empty patch of sky. And after all of that, we call it integration time or exposure time, enough photons from really distant objects in that patch of sky reached the Hubble Space Telescope, and we got the deep field image. Because that image, it looks like a black square with a bunch of fuzzy points of light on it. All of those points of light are galaxies. There are more than 3,000 galaxies in that little image alone. And so I'm really glad that Robert Williams completely, abused his power in this situation, because now we have the knowledge that the universe is much more densely packed and much more full of stuff than we thought it was before.
Yeah, that's really wild.
Yay.
Yay.
Yeah. Some other things that HST discovered. It provided evidence that nearly every galaxy in the universe has a supermassive black hole at its core. It taught us a lot about the nature of those black holes, how they behave. It even took some fuzzy images of the accretion disks around black holes, which you might remember are the hot, glowing disk of material that is actively falling into the black hole. Mm-hmm. And it also had this really cool discovery that black hole size, or the mass of your black hole, is dependent on the mass of the galaxy that hosts it. And maybe that's pretty intuitive, but we needed to learn that empirically. We needed data to support that hypothesis. So thank you, Hubble, for that.
Thank you, Hubble.
Hubble also mapped dark matter in the universe through gravitational lensing. So we talked about microlensing in our exoplanet detections episode. Gravitational lensing exists on many scales. And because we can't see dark matter, but we can observe how it interacts gravitationally, we were using the lensing effect of galaxies close to us to study invisible matter behind those galaxies and get an idea of how it's distributed throughout the universe, which is pretty cool. Hubble also allowed us to find and study exoplanets. It even got a look at some exoplanet atmospheres. One of the first times we discovered water in the atmosphere of an exoplanet was thanks to Hubble. And it studied bodies in our outer solar system. So it discovered 2 moons of Pluto before Pluto was demoted to a dwarf planet. So Hubble does everything. It does our solar system, it does stars, planets, galaxies, which makes sense because it just took $1.5 billion to make and launch. The upkeep and all the maintenance costs since 1990, we have spent about $16 billion on the Hubble Space Telescope.
That's a lot of money.
Oh, I think that's it, with some adjustment for inflation for the earlier years. But yeah, we spend a lot of money on this telescope. So we take care of it, and it does a lot of things.
Oh my God. I'm looking at some of the images it's taken, and they're so beautiful. It's crazy.
Oh, yeah. Soon people will start, I'm sure, if they aren't doing this already, people are going to start making AI art of space stuff.
Yes.
I don't like thinking about that, but
No.
But yeah, it's gorgeous. I was gonna say AI wishes it could make images that pretty, but it probably
probably will, yeah. But it's so nice to know that this is real and not made up.
Yeah, it is real. It is artists and scientists have gone into those images and added in color for
Right.
context. So even if you had eyes as powerful as the Hubble Space Telescope and you looked out at that source, that's not what you would see. But we try to add those colors so that you have an idea of what the image not looks like, but like what it is, like what really is happening out there.
Yeah, you can tell like something might be gaseous or dense or like moving or not based on the coloring. And I really love that.
Because really, when the telescope sends those 18 gigabytes of data back to Earth every week, it's not these pictures. It's not like printing out Polaroids and sending them. It's like arrays of numbers. It is, like values for how many photons hit a pixel in the camera's receptor. We do have to take that data and turn it into an image. So
that's really wild to me. I can't imagine how that's done.
There are now, luckily, a lot of tools, a lot of packages that have already been written in computer code to analyze the data and really quickly put out an image that astronomers and artists can work with after to make it really pretty. But a lot of that stuff has been automated.
Thank God.
Do you have any lingering questions about Hubble or anything it's done?
I am curious about when you're looking for a blank patch of space. Is that blank to the naked eye or blank to Hubble at first, and then though a long exposure will show more?
Oh, that's a good point. I think it's definitely blank to the naked eye, but I think it's mostly blank to whatever our catalogs say.
Okay.
They were looking for a patch of sky that, according to our catalogs of space, didn't have objects in it. They didn't use Hubble time to determine where to take the Hubble Deep Field image.
Yeah. Cool. It's such a pretty image.
Yeah. And the JWST one is even better, actually.
It? Of course
it is. Yeah, because JWST is bigger, so it's collecting more photons.
Well, there's a very fun page on NASA where you can look up what Hubble saw on your birthday.
Oh, let's do it.
So on
what did it see on your birthday?
Okay, on July 29th. And you don't pick the year, so it just shows you what it saw on a day this year. Or on that day, any year. It saw star cluster Trumpler 14 on my birthday. And it is a cluster of stars located 8,000 light years away. Trumpler is one of the worst words I've ever heard. And
yeah, I don't like it.
But the image is very glittery, lots of purples and browns and really glittery. I actually love this image. So I'll put it on our Instagram too. And Moiya, you're January, right?
Yeah, the 8th. Someone after the stand-up show I did on Friday, someone came up to me and was like, "You have strong Capricorn energy." Yeah.
Did you mention your birthday during it at all, or they just guessed you were a Capricorn?
Afterwards, when I was chatting with someone, I mentioned my birthday, and I think they overheard, and then they're like, "Oh yeah, that makes sense. You have strong Capricorn energy." Yeah.
Okay, on your birthday, they saw Galaxy NGC 2976. This picture is from 2007, and it shows the inner region of NGC 2976. Located 11 million light years away in the constellation Ursa Major.
I can't imagine that's a very pretty image.
It's very grainy. It's not my favorite. I wish there was a regenerate button where you could be show me a different one.
Yeah, that is pretty grainy. That's what you're going to get with the NGCs because they are irregular. A lot of them are irregular little galaxies, so they're not going to be pretty swirls.
Well,
nice, and it's so far away, so it's big Capricorn energy, yeah. All right, well, I need to go get some logs to add to this fire.
Yes.
So I think we should wrap up this episode.
Let's do it.
But, no matter where you are, no matter what NASA or the Hubble Space Telescope observed on your birthday, remember, you are space.
It's true. Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.